All right. So I'm Rick Edmondson. I am a card carrying mass spectrometrist, and so that's why we put the mass spectrometry talk at the beginning, because if I put it at the end, everybody would sleep through it. But we're hoping the excitement of the day lets you trudge through the next 20 minutes. And so I've been doing mass spectrometry a long time, but J.J. Thomson was doing it before I was. And so as a card carrying mass spectrometrist, I have to show the first mass spectrometer or a diagram of it. And so in a vacuum tube, you could separate out the isotopes of neon. And so pretty cool kind of to think where we've come from, where we've gone in terms of mass spectrometry and being biologically useful. So just an overview of what I'm going to talk about. I'm going to give kind of the basics of the mass spectrometer, talk about the ionization methods, and mainly electrospray. I mentioned MALDI because I have to talk about the types of mass spectrometers, and then just a quick glimpse at some carbon isotopes. And so I like to hear myself talk because nobody else does. And so I am going to do my best to try to get us back on track and get through this pretty quickly. And so the first thing you need to know is a mass spectrometer is a black box. And so a lot of them actually come in the color black, and it's fitting. But they do have a few parts that are at least useful to know. One starts with an ionization source, and I'll get into why that's so important. But we have to get our sample into the gas phase somehow. We have a mass chamber, a mass analyzer that's under vacuum, and so the vacuum in this is not unlike the vacuum in space. And so we evacuate all the air so that the ions don't run into gas molecules as they traverse through the instrument. We have to have some type of detector, so we have to measure these ions, and then a data system to collect them. The first thing you have to remember about a mass spectrometer is that the name is a little misleading because it doesn't measure mass. It measures mass to charge, and so it measures ions. In mass spectrometry, the Thomson is a unit of mass to charge, and so we talk about things. We'll throw around terms like Daltons, which is a atomic mass unit. They are very similar to a Thomson when the charge is 1, but when you're looking at a mass spectrometer, you're actually looking at a mass to charge scale. The ionization methods that really made it possible for a mass spectrometer to be used with biological samples were MALDI, or matrix-assisted laser desorption ionization, which really now is only being used in proteomics to do tissue imaging. It is, it's still viable, and it hurts me a little bit because my doctoral work was on that. So if anybody wants to know, if you're just curious about gas phase, acidity or basicity of organic molecules and how they transfer charge, I can put you to sleep. But the real meaningful technique now is electrospray. And so this was, it seemed like not long ago, but this really shows my age. So the Nobel Prize in 2002 was awarded to a couple of scientists. Actually, these two shared half the prize for coming up with these soft ionization techniques that allow us to put big molecules in the gas phase. And so we're doing electrospray ionization, which is a fancy term for hooking up liquid to a really small hole and applying voltage to it. You can see that the picture at the bottom is a picture of the spray cone that you get when you flow through roughly a 10 micron hole at a couple of hundred nanoliters a minute. And so you get these little micro droplets formed, and then from those micro droplets, you get smaller droplets that are ejected from the surface, and the solvent starts to boil off, and you end up with charge that's on the surface of the water molecule. And eventually this boils down till you get your analyte, or your peptide or protein, whatever is in your solution, and it has charges on it. Because this is a liquid flowing technique, it's easy to couple to an HPLC, and this is really how most modern biological mass spectrometers work. There are several different types of mass analyzers. The quadrupole ion trap was developed in the mid-2000s, and this is really kind of a workhorse instrument. Works really well there aren't any moving parts, and so they're pretty robust. And this, allowed mass spectrometers to be made and sold and put in labs that were not driven by people who had their degrees in mass spectrometry. And so this really kind of led to the growth of the field and what we know as proteomics today. If this animation works, and looks like it may, this kind of gives you a picture of how ion traps work. And so you can think of a saddle and trying to balance a golf ball on the peak of a saddle. If you were good enough about, and this is where, if I were in front of you, I could jostle with my hands, but I'm not going to try. But you could move the horns of a saddle around to keep that golf ball on the top, and that's what an ion trap's doing. It's moving electric fields, and so the ion is going to be attracted to an opposite charge, so a positively charged ion. It's going to be attracted to a negative charge. It's going to be repelled from a positive charge. So by alternating these charges, you can control an ion, and based on its mass to charge, it will move further. And so this is the principle that allows us to separate masses in a mass spectrometer. Fast forward a few years, a really bright Russian scientist in a small company came up with the idea of a new type of mass spectrometer, where it's not a magnetic field, but just a highly concentrated electric field. The ions move and allow you to get very high resolution. So you're measuring these ions, you're measuring the frequency that they move about an electrode. The nice thing about anything analytical where you're measuring frequency is you can measure it very precisely, because frequency, you get a chance to look at it over a long period of time. And so because of this precision, you can then get good accuracy. And so you can get high resolution, high accurate mass, and the sensitivity is really good. So you can get down to really measuring single ions. This is really it's amazing, considering the first scientific presentation happened in 1999, and they had a commercial instrument in 2005. And so that's lightning quick for an invention, and then getting it in the hands of users. We have lots of Thermo mass spectrometers in the lab. They're all of their newest instruments, and so this is really what allows us to offer something kind of unique to researchers, especially in IDeA states, is that we have the cutting edge instrument, the top of the line, that are often only in elite research labs. We have the ability to run somebody's sample, their very first proteomics experiment, on a multi-million-dollar mass spectrometer. I'm going to go skip through this because it's just going to take too long. I am going to show this, and so we have two things here that cost $1.2 million. One is expensive and fast when it works, but when it breaks down, it's very costly, and it's always broken down. And the other one is a car. And so, this is where, if I were in the room, I could hear you not laughing, but now with Zoom, I can also hear you not laughing. Mass spectrometers they're a lot like cars, and so the higher end they are, they don't always work. We try to run them around the clock, but there is an issue, and so we have one instrument in the lab that I feel like that we have joint custody between us and the service engineer that's working on it. He gets it 5 days a week, and we get it like 2 days a week, and so but when they work really well, just like the race car. And so so mass spectrometry experiments start, we have to get the ions into the gas phase. The mass analyzers allow us to separate their mass to charge ratio. A couple of different types: quadrupoles, ion traps, Orbitraps are the newest version of this. And through the years, the instruments always get faster and more sensitive, and so they're able to handle more complex mixtures that we throw at them. I'm going to talk just a little bit about isotopes, and so if you look at this is a peptide, and you notice there are several peaks there. This is one peptide, but several peaks. And so why are there several peaks? If we look at the periodic table of elements, we know that there are stable isotopes that occur in nature. Carbon has roughly 1% of carbon has an extra neutron, and so it's carbon-13. And so if you string enough carbons together, odds are one of those carbons is going to have a carbon-13. And so that's what you get when you see this. And so this peptide has 45 carbons, and there's about a 50% signal there that has one extra neutron in that carbon. As you get longer and longer peptide chains, so once you string together 112 carbons, now the most intense ion is that second peak, that second isotope. If you get even bigger, so this is one with 275 carbons, so now it's the fourth isotope that's the most abundant. And so I just show this to show a little bit of the complexity in this, and also the power, the resolution of these instruments, so that we can separate out individual isotopes in the mass spectrometer. But it actually gets even more impressive than that. And so now I'm gonna spend like just 2 minutes, just because I can bring up Einstein in everyday life, and anytime you can do that, it's a good day. But I'm gonna have to admit that, Einstein said if you can't explain it to a 6-year-old, you don't understand it yourself. I tried this. I actually cheated. I tried with a 7-year-old, a 7-year-old foster son. I tried to explain this to him, and it didn't go well. I did manage to explain it to my 23-year-old son, but granted, he's in an MD PhD program, and so maybe that's maybe he understood before I started explaining it. Back at looking at the monoisotopic masses, one thing you can see is that the mass, if you add a neutron to carbon, you get carbon-13. If you add another one, you get close to nitrogen-14, but it's a little bit off. This is actually a spectrum of a tag that we're going to talk about a little bit later, where we label these proteins with known isotopic elements, and we can, the mass spectrometer is good enough to distinguish between a mass that's 127.125 and 127.131. And this is the carbon-13 or the nitrogen-15 isotope that essentially both weigh 127. It's really neat that we can do this because it allows to multiplex, but why is that? Why, we had a couple of neutrons, why don't they both weigh the same? And why would we want to worry about this? Well, the mass accuracy is really high. It's greater than 1 part per million. But really, my reason for showing all of this to you is to try to help you remember, if you're ever doing something and you're looking at adding a tag onto a molecule, when you add up the elemental composition, you need to use as many decimal places as you can, and it probably needs to be at least 5 for the isotopes, because if you don't, the mass spectrometer is going to get the wrong answer. So it's precise enough that you need as many isotopes, as many numbers after the decimal as you can. And if we take oxygen as an example, and we take the mass, we know the mass of a proton, the neutron, and the electron. And if we add up those masses, we get a mass that's like 16.13, but oxygen's mass is 15.99. And so the difference here, this is where if we were in the room, I could, get the smart physics geek to raise their hand and go, I know why that is, but I'll have to call on Dennis. No, I won't do that now. The reason this is because nuclear binding energy. So there's a price. You always, nothing's free. So there's a price for holding those things in the nucleus. And so depending on the composition, carbon is different than nitrogen. And so the amount of nuclear binding energy is slightly different. And because Einstein equals mc squared, we can actually calculate this. So based on the mass difference, we can calculate the nuclear binding energy. I just think that's pretty cool. If you want to know more about it, I did include just this little blurb. You can look back at the slides to if you're, want to impress your friends and talk about mass defects and mass sufficiency. But the take home is that the precision and accuracy of these instruments is so good that we can actually tell the difference between a carbon and a nitrogen that have the same mass. So, all right, I went through that like lightning quick, but hopefully fast enough that nobody fell asleep. And I think, I don't know if you want to try to take a few questions if there are any, Dennis, or
well,
I was lots of questions.
I was just going to tell you, I was just giving you the 2-minute warning, and you finished. So I think you felt the vibe there, but you left them on a high note. Right now, the only thing is, and you already had alluded to it, is they're interested in getting a copy of the slides, and I went ahead and said that was perfectly fine.
Absolutely.
So.
All right, so I am stopping my share.
Thank you. And I think next we're going to hear